I'm Gopal R, editor of MRS Bulletin, and today it's my pleasure to talk with Professor Young-Chang Joo of Seoul National University. Professor Joo is a full professor in the Department of Material Science and Engineering at Seoul National University, and he's also currently on the MRS Board of Directors. His research focuses on electronic materials and devices, including microstructures, and stress analysis of interconnect materials, electrical reliability, reliability in electronic packaging, and electrical steels. So Young-Chang, thank you today for talking with us. And today we want to focus on one of your recent review articles, which in Electronic Materials Letters, which is on reliability issues and solutions for flexible electronics under mechanical fatigue. Of course, flexible electronics represents a major area of research in materials today, and there are also many applications, including in many consumer products. So this review paper seems to be focused on mechanical reliability, which is one specific area. So what are the new reliability issues for flexible devices as compared to conventional electronics?
Okay, thanks, Gopal. You have mentioned that, as you mentioned, the flexible electronics is increased to use, but the major difference between the conventional electronics and flexible devices is that they are under the constant mechanical deformation or mechanical stresses, such as bending, rolling, or even twisting, or some stretchings. In such conditions, we should ensure the device reliability. Such reliability is not only mentioned about the mechanical fracture, but also we should ensure that electrical performance should be ensured during the lifetime. So electromechanical property of the devices is getting more and more important.
So in particular, in terms of mechanical fatigue, what did you find was the most crucial issue or a few crucial issues in terms of reliability?
Yeah. Flexible devices is composed of various materials, metals or polymers, and often they have different mechanical behavior. So such hybrid structure have completely different mechanical property than they are single component. So we should understand how it behaves under such hybrid structure. For example, metals, which of course used as a conductor, have different mechanical property by changing the thickness, also the line width, and it also changes mechanical property or electrical property when it has different multilayers, like overlayers or top layer. Also processing condition, where it is vacuum deposited or like printed. So we should understand that. Second important issue for the mechanical fatigue testing is that the testing methodology also influences the lifetime, and we do not understand what is the right testing methodology. For example, people talked about the bending. Such simple bending, there are various ways to testing the bending test, like free bending or guided bending or sliding, and all give a different mechanical component in there. So we should understand their mechanical properties.
Of course, for any applications and real applications in industry, standards are very important.
Yeah.
So are there international standards under consideration for flexible devices with regard to reliability issues?
Yeah. Researchers in academia as well as the industry realize that the testing methodology is quite important to assess the lifetime, but there is no standard on it. So people is working on to set up the standard. They are grouped by different application, like flexible device such as a display, batteries, semiconductors, or OLED, or sensors, or printed film have grouped working on the international standard, and researchers from Europe, United States, Europe, or Asia is working together to set up the international standard.
Okay, very good. How can we improve the reliability of flexible devices, and in particular, what kind of research directions do you think are important for flexible devices today?
Yeah, that's very interesting question. Everybody wants to increase the reliability. But in order to increase the reliability, we should find out the mechanism. You should understand the mechanism. We found out that the in situ testing, that means that while the mechanical damage, monitor the electrical property during the in situ is quite helpful for understanding the mechanism. So once you understand the mechanism, then you apply all the known knowledge to the device integration, like a design, or processing methodology, or set up the environment to use it, then you can find out the way to improve the reliability, I think.
Okay. So your paper mentions methods for improving reliability using nanostructures, such as nanoholes, nanopores, nanowires, and multilayer structures. So this is very interesting. I was wondering if you could explain some of these approaches briefly.
Conventional wisdom as a defect, as a material scientist, is a bad thing for the reliability. But interestingly, we find out that if the metal film or line has uniformly distributed nanostructures, holes, or pores, it improves the reliability very great amount. We find out that the reason for improved reliability as such a uniformly dispersed nanoholes or nanopores is because that the mechanical damage in the line is caused by the irreversible motion of the dislocation. However, if there is nanoholes, they prevent the dislocation motion of the structures, then it prevents the accumulation of the dislocations. And also, even the cracks are generated when they propagating, they meet such nanoholes and nanopores. The whole crack tip is blunted, so they stop propagating. So this can help the reliability a lot.
So Professor Joo, I know you have a fairly large research group at Seoul National University, and I wonder if you'd like to talk about some of the other research areas that your group is involved with.
Yes, thanks, Rao. As our group also focusing on the stretchable electronics is the next thing on the flexible devices. And stretchable devices requires a completely different materials as a conductor or dielectric. We are developing new type of conductor which can tune this Poisson's ratio by incorporating the auxetic structure inside of the dielectric. The other area we are also doing is that developing new nanomaterials which can be applicable for the energy and environment issues, which the way we are doing is that we consider the thermodynamics and kinetics for the processing of these devices, and you make a nanostructure which can be suitable for such applications.
Well, we look forward to hearing more about these areas in the future. Thank you very much, Young-Chang, for talking with us today.
Thank you.